In this video, we are going to see how to derive the expression for electric field of a charged particle by using Gauss's law. So first, let's just consider a positively charged object, which is shown in the diagram. We want to find, let's say, electric field at point P, which is outside the charged object. And the distance between the object and the charged particle is r. The point and the charged particle is r. So we'll draw a Gaussian surface around the charged particle at which is passing through point P. So the Gaussian surface passes through point P and it encloses the charged particle. So now Gauss's law states that net flux is equal to Q in over epsilon. Now Q in, we can see that in this case is all of the charge because the whole charge is enclosed by the Gaussian surface. So we can replace Q in by Q. And phi net, we know that it is closed integral E dot dA. Now that's equal to Q over epsilon naught. Now for electric field direction, let's check on the diagram. The electric field direction shown by the black arrow is at point P is pointing outward. And the area vector at point P is also pointing outward. So area vector is perpendicular to the surface. So at point P, it will be pointing outwards. So we can see that area vector and electric field, they both are parallel to each other. That means the angle is 0. So cosine 0 will be equal to 1. And we can replace the dot product by EDA. That means you can see in this equation, we don't have vectors. We just have E and dA. So closed integral of EDA is equal to Q over epsilon. Now, we can take E out because electric field at a given distance will be constant. So we can take E out. So we are left with dA. And that's E closed integral dA equal to Q over epsilon. Now, this closed integral of dA is the total surface area of the sphere. That means we can use the formula for surface area of sphere, which is 4 pi r square. So we can replace dA, closed integral dA by 4 pi r square, and then rearrange the equation to get electric field. So you can see I've taken 4 pi r square on the other side. It comes in the denominator. And then in the last final step, we are just keeping the constants together. So 4 pi epsilon, we have made it together and r square is separate. Then 1 over 4 pi epsilon is k. So we can replace that by k. So we get the formula as kq over r square. Okay, I think it should be kq over r square. So that's kq over r square. Then this is for a point which is outside the charged particle. Now if the point is inside the charged object, then we'll draw the Gaussian surface inside, and A is the radius of the real sphere, whereas R is the radius of the Gaussian sphere. And we know that the dotted circle is the Gaussian surface. Now, the whole charge on the object is Q, but inside the Gaussian surface, we'll not have all the charge Q. We'll have just the charge which is inside the surface, so it is Q in. Now we are going to write Q in is equal to Q naught over A cube times R cube. This is by proportion of the volume. So you can use proportionality here because it's uniformly spread. So you can use ratio and proportion to get this. Q in is equal to Q naught over A cube times R cube. Now Gauss's law states that phi net equal to Q in over epsilon. We repeat and we substitute Q in by its formula. Now phi net can be written as closed integral E dot dA, theta is equal to 0. We can write it as EDA, closed integral EDA, we replace it. We take E out and then dA, closed integral dA will be 4 pi r square, exactly like what we did before, which is equal to QR cube over A cube epsilon. We bring the 4 pi r square down and the r square will cut to r square from the top, from the r cube, and we will be left with 1 r on the top. So we can keep all the constants together, Q over 4 pi epsilon A cube times r. And then we can write 1 over 4 pi epsilon as k. So we get kq over A cube times r. That's how we derive the formula for electric field using Gauss's law.